We want to demonstrate the graphing of linear functions. And basically, a linear function is a linear equation. And the difference between the traditional equations that we've expressed in slope-intercept form, so we have written equations that look like y is equal to mx plus b. And these equations are similar, except that y is replaced with f of x, and m, the slope, is replaced with the coefficient a, which is the coefficient of x, and then the b, which is the constant, are the same. We represent the equation in this format, the function notation, because we want to demonstrate that f of x, the y value, is dependent on the x, which is why we put it inside these parentheses. And so we are saying this is a function which changes when x changes. And it's true that the y value does change when the x changes, but again, we want to emphasize that in this particular equation. So in this example, we're asked to write this equation as a linear function and graph it. So what we want to do is write it in the format with f of x on one side of the equation and then the x term and the constant on the other. And realizing that y represents f of x, we want to isolate that y. So when we start off with the equation, x plus 2y is equal to 6, we are targeting that y, so we'll subtract off the x from both sides, and we get 2y is equal to, and I'm going to write the x term first, so I've got negative x plus 6. And finally, to isolate that y, we will divide by 2, so we have to divide every term by 2. And when we get the equation, we end up with then that y is equal to negative 1/2, that's the coefficient on x, and then plus 3. And our final step is then to replace the y with f of x. So we've got f of x is equal to negative 1/2 x plus 3. And this does fit the format of the linear function. We've got f of x on the left, we've got an x term with a coefficient on the right-hand side, and then we've got the constant term. So now that we've got the function, we can graph it, and we can use the slope-intercept form of this equation. So we've got y, or f of x, is equal to mx plus b. So this positive 3 is our b, which is our y-coordinate of the y-intercept, and the y-intercept is the point 0, 3. So I can go ahead and graph that. And next I'm going to use my slope, which is negative 1/2, and I'm going to write that as negative 1 divided by 2 as a means of counting to find another point. If I look at this as rise over run, I can say that the rise is in the numerator, and rise of negative 1 means we're actually going down, and so we're going down 1 unit, and the denominator, the run of 2, means that positive 2 is going in the right direction. So I can use this counting to count from the anchor point, the y-intercept that I started with, and if I count down 1 and go 2 to the right, I can place another point here, and 1 down, 2 to the right, and so on. And if I connect the dots, then I get the graph of the function. We can take a quick look over of the line to see whether it's what we'd expect. From the equation, we've got f of x, or y, is equal to negative 1/2 x plus 3, and the slope of negative 1/2 means that this line should be falling as we go from left to right, and it also should be falling somewhat gradually because we are going to the right 2 units for every 1 unit that we go down, and that is what we expect. With the y-intercept at positive 3, we hit the axis at positive 3, and again that's consistent with what we would expect.